Our universe is constantly expanding, stretching the fabric of space-time in all directions. This growth, driven by dark energy, a mysterious force counteracting gravity, causes galaxies to move apart faster over time. Scientists track this expansion using redshift, where light from distant galaxies stretches into longer wavelengths as space itself expands. The Big Bang theory, supported by evidence like the cosmic microwave background, CMB, suggests the universe began 13.8 billion years ago as a hot, dense point. Yet, its ultimate fate, whether it will expand endlessly or collapse, remains debated, hinging on the balance between dark energy and gravity. The James Webb Space Telescope, JWST, launched in 2021, has revolutionized astronomy by observing infrared light invisible to human eyes. Unlike Hubble, which captures visible and ultraviolet light, JWST's 6.5-meter gold-coated mirror detects faint signals from the universe's first stars and galaxies. Its NIRCam and MIRI instruments have identified water vapor on exoplanets and carbon molecules in distant nebulae. For example, JWST recently spotted Glass Z13, a galaxy formed just 300 million years after the Big Bang, reshaping theories about early cosmic evolution. Physicist Brian Cox often highlights that the observable universe spans 93 billion light-years, a bubble limited by light's travel time since the Big Bang. Beyond this lies the unobservable universe, potentially infinite and filled with galaxies we may never see. The CMB, a faint glow from 380,000 years after the Big Bang, acts as a cosmic snapshot. Tiny temperature fluctuations in the CMB reveal density variations that seeded galaxies, mapped by missions like Planck and WMAP. Within the observable universe, astronomers estimate there are 2 trillion galaxies, each hosting billions of stars. The Hubble Ultra Deep Field image, which captured 10,000 galaxies in a sky area the size of a grain of sand, underscores this immense density. Yet, dark matter, 27% of the universe, and dark energy, 68%, dominate its composition, leaving visible matter, stars, planets, and gas, at just 5%. Dark matter's gravity binds galaxies, while dark energy drives cosmic acceleration, creating a tug-of-war that shapes the universe's fate. Our solar system, though vast, is minuscule within the Milky Way. At 70 miles per hour, a trip to Neptune would take 4,400 years, longer than recorded human history. Voyager 1, launched in 1977, exited the heliosphere, the Sun's influence, in 2012, entering interstellar space at 38,000 miles per hour. Even at this speed, reaching the Oort cloud, the solar system's edge, would take 300 years, highlighting the challenges of interstellar exploration. The Milky Way, with 300 billion stars, includes diverse systems from red dwarfs to blue giants. Proxima Centauri, our nearest star, is 4.24 light-years away, a 40 trillion kilometer journey. At Voyager's speed, the trip would take 70,000 years, underscoring the need for breakthroughs like nuclear propulsion or light sails. Projects like Breakthrough Starshot aim to send microprobes at 20% light speed, reaching Alpha Centauri in 20 years, though technical hurdles remain. Vega, a bright star 25 light-years away, exemplifies how light carries ancient history. When we observe Vega, we see it as it was during the Renaissance. Meanwhile, Earth's radio broadcasts, like I Love Lucy, have traveled 150 light-years, reaching 15,000 star systems. Yet, this sphere is tiny compared to the Milky Way's 100,000 light-year diameter, emphasizing our cosmic isolation. If the solar system were a quarter, the Milky Way would stretch across the continental US, with each star a speck of dust. The Andromeda galaxy, 2.5 million light-years away, is racing toward us at 110 kilometers per second, set to collide with the Milky Way in 4.5 billion years. This merger will birth Milkomeda, a giant elliptical galaxy. Though stars are so spaced that direct collisions are rare, gas clouds will compress, sparking new star formation. Galactic collisions might spread organic molecules via panspermia, where life's building blocks hitchhike on comets. The late heavy bombardment, 4 billion years ago, saw asteroids deliver water and amino acids to Earth, suggesting life's ingredients could survive interstellar journeys. Extremophiles like tardigrades demonstrate that life can endure space's harshness, hinting at possible interstellar migration. Our local group, a cluster of 54 galaxies, includes the Milky Way, Andromeda, and the Triangulum Galaxy. This group orbits the Virgo cluster, a collection of 1,500 galaxies 54 million light-years away. Virgo itself is part of the Laniakea supercluster, a vast network of 100,000 galaxies spanning 520 million light-years. These structures form the cosmic web, a network of filaments and voids shaped by dark matter's gravity. Cosmic voids, like the Boötes void, span 330 million light-years and contain few galaxies, contrasting with dense filaments of gas and galaxies. The cosmic web originated from quantum fluctuations in the early universe, magnified by inflation. Simulations like Illustri's TNG recreate this structure, showing how dark matters pull sculpted galaxies over eons. Supernovae, exploding stars, forge elements like iron, gold, and uranium, scattering them into space. A single Type II supernova outshines its galaxy for weeks, releasing energy equal to the Sun's 10 billion-year output. These explosions create neutron stars and black holes, remnants with extreme densities, where a sugar cube-sized piece would weigh 1 billion tons. Black holes range from stellar mass to supermassive varieties anchoring galaxies. Sagittarius A, the Milky Way's central black hole, weighs 4 million solar masses. When black holes merge, they emit gravitational waves, ripples in spacetime detected by LIGO and Virgo. These events release more energy than all stars combined, proving Einstein's predictions. Beyond the observable universe lies the unobservable cosmos, possibly infinite, with regions receding faster than light can reach us. Theories like eternal inflation suggest our universe is one of countless bubble universes in a multiverse. Each bubble could have different physical laws, making life possible only in rare Goldilocks zones. While unproven, this idea challenges our perception of cosmic uniqueness, sparking debates about fine-tuning and the anthropic principle. Humanity's atoms, carbon, oxygen, iron, were forged in ancient stars and supernovae. We are stardust, a testament to the universe's self-awareness. The JWST and upcoming telescopes like the Nancy Grace Roman Space Telescope will search for biosignatures, oxygen and methane, on exoplanets. Discovering life, even microbial, would redefine our cosmic significance, answering whether we are alone or part of a grand universal story.